Binary cross entropy loss. Let us learn about BCE or binary cross entropy, which is the most widely used loss function in classification tasks, especially when the target variable is binary. Binary means 0 or 1. If you want to predict between two classes, one is 0, other is 1, then you generally used binary cross entropy as your loss function. What we'll do is we'll understand what is this loss function. We'll do complete derivation. We'll understand how exactly this comes. What is the logic behind this loss function? How is it actually coming up as a useful loss function? How is it calculating the loss? How can you find the gradients? All those things we'll go through. First thing you should be clear about, what is the logic behind using this particular loss function? You should not simply see it like a formula. The formula should make logical sense for you. That is what we are focusing on. First thing, we'll first see all the terminology that we are going to use in this lecture so that you won't be confused about what is y cap, these things. Okay. First thing we want to be clear about, x. X is your input. X is your input. Whatever is the input that is given, that you will call as x. Next one is y. Y is true label. That is, if you have a model and you are passing input x, what is the true label that is expected? Y cap will be what the model actually outputs, but what is the true label that you want? That is called as y. So y will take only two values. One is 0 and the other is 1. Why is y taking only two values? Because we are taking a classification task. It is a classification task with only two classes. First class you will call as 0. The second class you will call as 1. So your output will always be either 0 or 1. If you are having any input x, this x has to be classified as class 0 or class 1. So your y will be one value. Either it will be 0 or it will be 1. Next thing is theta. Theta is model parameters. Model parameters. So actually this theta is what you want to find out. You are training the model so that you can find out the right values of theta. If the model has the right values of theta, then when you pass x through the model, you will get correct value of y. So theta is what you want to find out. You are training the model so that model parameter theta can be found out. Next thing is y cap. Y cap, this is the output. When I say output, what is the difference with true label? True label is actually the exact class that each data belong to, but true label is the numerical value that your model is going to output. If you have a model M, you are passing the input X through this model. Whatever this model gave you as output, that you call as Y cap. So this Y cap won't simply be a value of 0 or 1. Instead, Y cap can take any value from 0 to 1. So this is the difference between Y and Y cap. Y is the true label which will take either 0 or 1. But y cap is the model output. It can take any value from 0 to 1. So what are you going to do with this y cap? Y cap, you are going to interpret y cap as the probability that input x is belonging to class 1. What will that do? If you assume that whatever is y cap, it will be a value between 0 and 1. So let us say you got 0.87. What does this mean? If you interpret this as the probability that your input is belonging to class 1, then this output y cap tells you that 87% chances are that the input that is given x, that is belonging to class 1, which will automatically tell you that 13% is the chance that this particular input x is belonging to class 0. So this is how you are going to interpret the model output y cap. This is how you do in a classification task. Okay. This part should be clear for you. Then only you will understand what is the logic behind the mathematics we are doing. Whatever equations, formulas we have for binary cross entropy, that will make sense for you only if you're clear with this part. What exactly are these terminologies? What these things mean? Okay. Now that you are clear of this, next thing I'm going to do is let us write y cap first. What is y cap? What did I say? I'm just going to write whatever I told just now mathematically. What did I say? I said y cap is the probability that data x belongs to class 1. So I will write it as probability of y is equal to 1. That is class is 1. Y is equal to 1 given what are the given values? X, which is the data, is given, and theta is also given. That is model parameter theta. So given these two, then in the model you are assuming, in the previous lectures we told that theta is what we were finding out. So that is why I am clarifying. In the model, when you are passing input through the model, taking the output, you are saying, I know some theta that is there in the model. I know x that is given as input. Now I want y cap, which is the probability that this x will belong to class 1. So that is what I am writing here. So for y cap, you will say probability of y equal to 1 given x and theta. Okay. So this value, keep in mind, this will belong to 0 to 1. Okay. This is about y cap. True label y, this will be either 0 or 1. It can't take values in between. Okay. What I'll do now is, firstly, I'll directly write the BCE formula. That is binary cross entropy. I'll directly write the formula. The reason is I want that formula to be there in your mind. Then we'll go and explain what is the logic behind this, how each term comes up, what is the significance of each terms, and how should you actually understand that BCE formula. We'll do complete derivation as well. Okay. So first thing I'm going to write is, you want the likelihood. So considering a single training example in which you have input x, I am going to write the likelihood of y cap. This I can write as minus of, as of now just see the formula, I'll explain later. Okay, minus of y log y cap plus 1 minus y log 1 minus y cap. So this is the formula for binary cross entropy loss. For now, I just want you to be familiar with the formula. Then we'll see how exactly this formula is coming. What does this mean? Okay. This is for a single training example. Instead, generally you won't be having just a single training example. You will have n examples. So considering that BCE loss, binary cross entropy loss, this can be written as minus 1 by n, that is for n training examples, I am writing this, 1 by n sigma I is equal to 1 to n. Then I will say for each of the ith example, I am taking yi. What does yi mean? Yi means the true label for the ith example. Yi log yi cap plus 1 minus yi log 1 minus yi cap. So this is my BCE formula. As of now, just keep in mind that this is the BCE formula. We'll explain each of these parts. We'll derive the whole thing. We'll explain the significance of each of these terms in the formula. For now, just see this formula. I want you to be familiar with this so that when we derive, you should suddenly have that realization that, okay, I reached this particular formula by using this logic. So that is why we are doing this. Okay, so this is the BCE loss. Let us see the logic behind. Mainly, we are going to use maximum likelihood estimation. So now you will understand why I covered maximum likelihood estimation in the last lecture. Last two lectures, we covered likelihood and maximum likelihood estimation. So if you miss those, please go and watch those so that you will be more clear with whatever we are going to explain. Okay. the concept of maximum likelihood estimate that is explained in the previous lecture. We are going to use that logic and then we are going to build BCE loss. Okay. First thing, I want to define loss here. What are we going to take as loss? So under the assumption that data follows Bernoulli distribution, we are going to just define what could be the loss in this scenario. Let us say y is equal to 1. So if y is equal to 1, y is equal to 1 means the true label for this particular input is 1. It should actually belong to class 1. Then I will say probability is y cap. Why is it probability? Because this is the output of the model. So output of the model is interpreted as the probability that input belongs to class 1. So if input belongs to class 1, then the probability that it belongs to class 1 according to the model it is y cap, right? So the probability is then y cap. I'll write probability is equal to y cap. Then how should I express loss? Just think about this. Just come up with an idea. How should I actually express the loss that is happening in this particular input? Let us say I gave some input x, model took this input, it gave some output y cap. I know y is the true label. I know y cap is the probability that input x should belong to the true label according to the model. Now I want to evaluate this y cap and tell the model this is the loss. This much is the loss that you caused in this particular output. When you prepared this output, this is the loss that you caused. I want to tell that to the model. So one logic I can use is I can take log of y cap. If I take log of y cap, what happens? You know, log of 1 is 0. If I take log of 0, that will be minus infinity. But in between, if I take values between 1 to 0, the value of log will go from 0 to minus infinity. So it will keep increasing. So if I take any value in between, according to the magnitude of that value, the log of that value will have a magnitude from 0 to minus infinity. So as of now, just understand that as your y cap moves from 1 to 0, log y cap will move from 0 to minus infinity. So now think back. Now think, when y cap moves from 1 to 0, if I consider log y cap as the loss, will it be right? Is that logically right? This is what I want you to think. If I am having some particular value, let us say 0.8 as my y cap, then my log y cap will be something between 0 and minus infinity, but something closer to 0 than closer to minus infinity. Okay. Instead, if I take something like, let us say 0.2, if my model outputted 0.2, so 0.8 is a better output than 0.2 because I know it is belonging to class 1. My model is saying 0.8%, 0.8 as probability, which means 80% probability. That is a better output than saying 20% probability. You agree with this? Then log of 0.8 will be a value closer to 0 and log of 0.2 will be a value which is closer to minus infinity, which means this value is closer to minus infinity, which means that is a smaller value. Even though it is larger in magnitude, because of the negative sign, it is considered a smaller value. Here for 0.8, because it is anyway a negative number but closer to 0, that will be a larger number than whatever you got for 0.2. This is logically the reverse of what you want. What do you actually want? You want that 0.2 case should notify that you made a larger loss here, because you should have given something close to 1. Instead, the model gave 0.2, which is very bad. Loss should be much larger here and loss should be smaller here. 0.8 should have given a smaller loss, which means the logic that you used here has to be reversed. How will you reverse? You simply put a negative sign, then it is reversed. This is how you can say that the loss for this particular case is minus log y cap. If it is minus log y cap, what happens? For 0.2, it will give a value close to minus infinity, which means a large number with a negative sign. That when added with this negative becomes positive, which means this case will give a very high loss value. This case will give a lower loss value. So this is the logic using which I am saying log interpreted as minus log y cap, loss interpreted as minus log y cap is a good idea. Okay. So just keep this in mind. I am just building different parts for the final solution. Let us take the other case. This is if y equal to 1. If your y is equal to 0, that is, let us say actually this belongs to class 0. Then what will be the probability? Probability will be 1 minus y cap. Why will it be 1 minus y cap? Because the definition of y cap will remain the same irrespective of your true label. Y cap is always treated as the probability that this particular input belongs to class 1 given belongs to class 1 given the data, given the input and the parameters. The probability that this input belongs to class 1, that is what you are calling as y cap. So what is the probability that it will belong to class 0? That will be 1 minus y cap, because if y cap is the probability that it belongs to class 1, then only one more class is remaining, class 0. So the probability that it belongs to class 0 should be 1 minus y cap. Then using the same logic that we used here, what could be a good option for loss? It can be minus log 1 minus y cap. So I am using the same logic that we used above. Using that, I know if the true label is class 1, then I can use loss as minus log y cap. And if true label is class 0, then I can use loss as minus log 1 minus y cap. This will be a good logic. What will this do? This would mean it would penalize confident but wrong predictions heavily. That is, if it actually belongs to class 1 and your model is confidently saying that probability is 0.1, that means it is confidently telling you that it is belonging to class 0, because 0.1 probability for class 1 means it is in class 0. It is confidently telling you it is class 0, but it is actually class 1. Then you should penalize it heavily. That is when this formula comes handy. Okay. Same in the other case as well when you're using for class 0. So this is one main logic you have to understand behind the BCE loss formula. Next thing, we are going to find out how exactly this formula came, how maximum likelihood estimate was used, how log likelihood was taken, how negative log likelihood reached. Those things we are going to understand. We'll also find out the gradient. Okay. So for this, the first thing is we discussed that probability of class 1, that should be y cap. So for each input yi, what will I write is yi cap. Yi cap means output of model for the ith particular input. That is what I'm calling as yi cap. This can be written as probability of theta is the parameter, model parameter, probability that yi is equal to 1, that is ith true label is 1, given the input xi. So this particular value, this will belong to 0 to 1. This we already discussed, you know this. So for a Bernoulli variable which is having this parameter yi, then probability mass function. How will you write probability mass function for a Bernoulli variable? This is the most important part here. So you can write it as P of, this is the probability mass function I am writing, yi given yi cap, yi given yi cap. This can be written as yi cap raised to yi. Keep in mind this yi will be a probability and sorry, yi cap will be a probability value between 0 and 1, and yi will be the label which will take values either 0 or 1 into 1 minus yi cap raised to 1 minus yi. So this is how you can write probability mass function for a Bernoulli variable. So if you generalize this, you can write it as P of y. Instead of the ith example, if you generalize, you can write as P of y given y cap is equal to y cap raised to y into 1 minus y cap raised to 1 minus y. Okay. So this thing, next thing I am going to do is, I am assuming that it is IID samples, and then I am going to take likelihood. When I take likelihood, what happens is, we already discussed likelihood formulas in the last 2 lectures. So I am directly writing likelihood here. I am hoping you'll understand this part. I have to take product of this, right? In the last lecture also we did it. In the likelihood lecture and maximum likelihood estimate lecture also we did it. So what are we going to do? You have to take product for all the samples. In case of one particular sample, ith example, you got this as the probability mass function. When you want to find out the likelihood, what will you take? You will take product pi I is equal to 1 to n over all the n samples, I equal to 1 to n. What do you want to do? P of probability of yi given yi cap. So this is the likelihood. How can this be written? This will be product I is equal to 1 to n. What is this particular value? I'll copy it directly from here. I will write it as yi cap raised to yi into 1 minus yi cap raised to 1 minus yi. So this is my likelihood. Okay, one thing you may think is, why did we not take mean squared error? Because in case of regression loss functions, many times we had said mean square error is a go-to thing. Why did we take this log here as error function? Why did I not consider mean squared error? The reason is, log I already explained why this is very efficient, why it is actually being a loss function. Just think, if you took mean squared error, what would have happened? What would have happened is, you would have taken one particular probability and you would have compared it with actual value. Then when you take, if you take gradient, what will happen is, for wrong and confident output, here we explained about wrong and confident output. When it is confidently saying 0.1 and it actually belongs to 1, how it actually penalized heavily. Whenever you are having wrong and confident output, you should penalize it heavily. Instead, if you took mean squared error, then when you take gradient, it would have come into normal linear terms, and then weaker predictions, that is gradient will become weaker for the predictions which are weak, that is wrong and confident. Which is wrong? Gradient should be higher when the predictions are weak, that is predictions when they are wrong and confident, you should get a higher gradient. And when the predictions are better, that is predictions are actually right and confident, you should have a weaker gradient. So this is what should actually happen. When we find the gradient, you will understand that better. That is why you should not go for mean squared error. Instead, you should go for the log error. So let's continue with this derivation. You will be clear at that point. This is the likelihood. Considering this likelihood, this is the likelihood function. What did we discuss in the last lectures? When you are going for the likelihood estimate, you always take the log likelihood. Why is it? Because log turns products into sum, which makes it numerically stable. So if I take log likelihood, log L theta. So this can be written as small l of theta. Log L theta, what will happen? I am going to take log of this, then product will turn to sum. It will be sigma I is equal to 1 to n. Then what will happen to this? Yi cap raised to yi. When I take log, it will become, I'm taking log, okay? Yi log yi cap. Because I took log on this, yi came to the left side, the exponentiation, it became product, and then whatever is product here, that will become sum. So this plus 1 minus yi 1 minus yi log 1 minus yi cap. So this is what happens when I take log. So this conversion, I hope it is clear for you. I directly did it because in last 2 lectures, we did it step by step. What happened is this product turned to sum when we took log, and then this here there is a product here. This is turned to sum, and this exponentiation, it turned to yi into log 1 minus y cap, and this one turned into 1 minus yi log 1 minus yi cap. Okay, so this is what happened when I took log likelihood. Next thing, what are we going to find? We want to take maximum likelihood is what we want to find out, which means you want to maximize this log likelihood. So instead of maximizing something, there is another method. That is, what I actually want to do is I want to maximize likelihood. In order to increase numerical stability, I converted it into log likelihood. Now I want to actually maximize this log likelihood. Instead, what I can do is, instead of maximizing something, I can minimize negative of the same thing. This is the logic I'm going to use. And for this, what I'm going to do is, instead of maximizing this log likelihood, I am going to take negative log likelihood. Then I can minimize it. Why do I want to minimize? Because we are actually finding BCE loss. That is binary cross entropy loss. Loss is something that you should always minimize. If you want the model to perform the best, then you should always minimize loss. You should not keep maximizing loss. Here, you are having log likelihood, which you should actually maximize if you want your model to perform better. But what are we finding out? We are finding out an equation for loss function. It is binary cross entropy loss. Loss should be minimized if you want your model to perform better. So for that, to find out the loss function, what I'll do is, now that I know I want to maximize log likelihood, instead I can also minimize negative of log likelihood. So I'll take negative log likelihood. I'll call it NLL, negative log likelihood. This is simply a negative sign put in front of this log likelihood. I equal to 1 to n. Then this will be yi log yi cap plus 1 minus yi into log 1 minus yi cap. So this is my negative log likelihood. Now I can directly see to minimize this negative log likelihood. When I minimize negative log likelihood, what happens? My model will perform better. My model parameter theta will improve. My model will perform better if I minimize negative of log likelihood. Next thing I'm going to do is, here I considered just one particular example, but ideally, here we are taking negative log likelihood. So what I want to do is, here I am considering just one particular example, the ith one, and then I took for n samples. When I actually want to find loss here, I don't want total loss. I don't want the summation of total loss. Instead, I want average of the total loss per example. Here I have n examples. I summed up the loss for all the examples and found out the total sum. But what I actually want is, I want just the average loss. That is, if you have n examples, then what is average loss or per example loss? For that, what I'll do is I'll take 1 by n of this particular value. That is what I'm going to call as BCE or log loss. So BCE, binary cross entropy, it is also called as log loss. BCE of theta, binary cross entropy loss, this will be minus 1 by n into sigma I is equal to 1 to n yi log 1 log yi cap yi log yi cap. I'm just copying whatever I wrote here. I'm copying. Just I put 1 by n in front. That is the only difference, so that I can find per example or the average value. For that I put a 1 by n. Otherwise I'm just copying whatever I wrote here. Okay. This into 1 minus yi log 1 minus yi cap. So this will be my binary cross entropy loss. This is the formula for binary cross entropy loss. Now what you can do is you can compare whatever we reached here with what I wrote in the beginning. This thing is exactly what we found out. We derived this particular binary cross entropy loss by starting from the beginning, going through what is the loss for each of the cases, y equal to 1, y equal to 0. Then we built it step by step, and finally we reached the formula for binary cross entropy loss. One more thing. Before we conclude the lecture, we'll do one more thing. We'll try to find out the gradient, because you should know how gradients are found for these examples. So I'll just show you how can you find the gradient for binary cross entropy loss. Okay, let us find the gradient here. I'll again write loss here. Okay, let's write loss. Loss is equal to, I'm just writing it generally, I'm not taking each yi here. Okay, so that mathematics becomes easier. Okay, I don't want to put all that 1 by n term. I'll write y log y cap plus 1 minus y log 1 minus y cap. So this is my binary cross entropy loss. I just avoided that 1 by n term and I generalized. So the steps for finding gradient will be same in either ways. Here it will be easier to deal with. Okay, what is the first thing I want to do? I want to find out the gradient with respect to y cap. That is what I want to find. What do I want to find? Del L by del y cap. Gradient with respect to y cap is what I want to find. First thing, I'll find this term's gradient. Then I'll find this term's gradient. Then I can simply sum them. That is the easiest way. So I'll take the first term's gradient. Okay. If I do d by dy cap, or if I write together, is it fine? Okay, I'll write del L by del y cap is equal to minus of, inside this what will I do? I'll write d, or I'll write minus inside as well. D by dy cap of minus y log y cap plus d by dy cap of minus 1 minus y log 1 minus y cap. This is what I am going to find out. What happens now? If I take this, here if I solve for this, what happens? I am taking gradient with respect to y cap. So y cap is inside log here. If you take gradient of log x, if you take derivative of log x, it will be 1 by x. So this will become minus y will stay as it is. Y cap will become 1 by y cap. So it will be minus y by y cap plus what will happen to this term? Minus of 1 minus y divided by what happens to this term? This will become 1 by 1 minus y cap. This will become 1 by 1 minus y cap. And then you have to take derivative of this term, 1 minus y cap. When you take derivative of this with respect to y cap, it will be minus 1. So here you will get minus 1. So this minus and this minus cancels out. So I'm removing both those. This will be the derivative. If you solve for this, what will you get? This will be, this will come up. So it will be y cap minus y divided by y cap into 1 minus y cap. So this is what you will get. So this is the derivative with respect to y cap. I just wanted to show you how to take the derivative of this BCE loss formula, BCE loss 1. So what we learned in this lecture, we learned about binary cross entropy loss, which is the most widely used loss function in classification task. That is, when you want binary classification, when you want to classify between two classes, class 0 and class 1, you always use binary cross entropy as your loss function. We explained what are the parameters, what are the logic behind this. Then this is the BCE formula. Then we went through each of the cases, what could be the better loss function, what could be a better mathematical way of expressing loss. Then we went to the likelihood function. We found out the likelihood. Then we found out log likelihood. Then we took negative log likelihood. That is how we reached BCE loss. This is the final formula for BCE loss. Then additionally, we found out the gradient of BCE loss as well. So this would complete the lecture on BCE loss. This is one very important lecture because binary cross entropy is very widely used, and it is important that you understand it logically rather than simply understanding the formula. You should know what is the logic behind it. So then when you write the formula, you will understand, okay, this is why I'm doing this, right? So that is it about binary cross entropy loss.